Okay, so for the naive algorithm, I've kind of drawn out what our matrix looks like, our m rows by n columns, and I've written out that what we want is the min values for each of the m rows, right? Sorry if that looks like wows, excuse my handwriting, but yeah, we want the min value for each of the m rows, right? So first, let's make like a result list where we'll store our results. And the most basic way to do this is, of course, to iterate through all of the m rows. So for I in range m, what we're going to do is we're just going to use a simple min function to find the min value of that particular row, right? And we're going to say result dot append the min value for that particular row of A, right? Of matrix A. So that particular row of matrix A can be indexed by the iterator, by the counter iterator I, right? And what this will do is what A of I is basically is just extracting a row of the 2D matrix given to us, right? So it'll give us A0, then A1 and so on. And the min value will just find the minimum value in that whole row. And then we'll just append that to the result and we'll return the result. Okay, sounds good. So I'm gonna clear the screen. Yeah. So we have a naive monotone coded out here. Let's see how it performs for some of the test matrices that we created below, above. And note that you can notice that I've included a percentage time symbol at the top of the cell. All this does is that it tells us how long that particular cell takes to run, right? So don't really worry if you don't understand what that means, but that'll just help us evaluate performance a bit, right? Okay, and we can also, once we run this, we can also compare these outputs to our expected outputs, see if it matches what we want. So test matrix small one, it gives us 1, 2, and 0. This is test matrix small one, this is 2, and this is 3. Remember that the expected outputs are 1, 2, 0, 1, 3, and 1, 1, 1. So we got our expected output for test matrix small one, for 2, and for 3, right? So great, a naive algorithm works. So why exactly would we want another algorithm, right? And here's why. Because enter a 10,000 by 10,000 matrix, and let's see how long this takes to run. As you can see, it's taking like a little while. Even for a modern day computer, this is just like 10,000 square values are not those many. But even then, this naive approach is taking really long to run. And as you can see, it's taken a wall time of 16.9 seconds to run this. So, and of course, the output is as expected. It's probably 10,000 zeros. I'm not going to count all of them. But yeah, it took 16.9 seconds to run, which is a lot, right? So that probably tells us that we need a much quicker and much better approach than this. So that's exactly what we're going to do in the next video. We're going to sort of talk about how we can make an efficient monotone finder, minimum value finder, right? And we'll code that up in efficient monotone.